Chapter 10. Magnetic fields due to electric current. Exercises pages 248 to 250. Exercises Q1.1, page 248. A conductor has three segments, two straight and of length L each and a semicircular with radius r. It carries a current I. What is the magnetic field B at point P? Solution. Exercises Q1.2, page 248. Choose the correct option. Figures A and B show 2 ampere loops associated with the conductors carrying current I in the sense shown. Solution. Micro 0 L, 0. Exercises Q1.3, page 248. Choose the correct option. A proton enters a uniform magnetic field B, directed into the plane of the page, perpendicularly along the positive axis with a velocity v, as shown. Then, it will follow the following path. The magnetic field is directed into the paper. 1. It will continue to move along positive axis. 2. It will move along a curved path, bending towards positive axis. 3. It will move along a curved path, bending towards negative axis. 4. It will move along a sinusoidal path along the positive axis. Solution. It will move along a curved path, bending towards positive axes. Exercises Q1.4, page 249. Choose the correct option. A conducting thick copper rod of length 1 meter carries a current of 15 A and is located on the Earth's equator. There the magnetic flux lines of Earth's magnetic field are horizontal, with the field of 1.3 x 10 to 4 t, south to north. The magnitude and direction of the force on the rod, when it is oriented so that current flows from west to east, are 1. 14 times 10 to 4 n, downward 2. 20 times 10 to 4 n, downward 3. 14 times 10 to 4 n, upward 4. 20 times 10 to 4 n, upward. Solution. 20 times 10 to 4 n, upward. Exercises Q1.5, page 249. A charged particle is in motion having initial velocity versus when it enters into a region of uniform magnetic field perpendicular to V. Because of the magnetic force, the kinetic energy of the particle will 1. Remain unchanged. 2. Get reduced. 3. Increase. 4. Be reduced to 0. Solution. Remain unchanged. Explanation. The magnetic force acts perpendicular to the velocity of the particle. This causes circular motion. In the magnetic field, the speed and kinetic energy of the particle remains constant, but the direction is altered at each instant by the perpendicular magnetic force. Hence the kinetic energy remains constant. Exercises Q2, page 249. A piece of straight wire has mass 20 grams and length 1 meter. It is to be levitated using a current of 1 A flowing through it and a perpendicular magnetic field B in a horizontal direction. What must be the magnitude B of the magnetic field? Solution. To balance the wire, the upward magnetic force must be equal in magnitude to the downward force due to gravity. Exercises Q3, page 249. Calculate the value of the magnetic field at a distance of 2 cm from a very long straight wire carrying a current of 5 A given. μ0 equals 4 pi times 10 to 7 Wb am. Solution. Exercises Q4, page 249. An electron is moving with a speed of 3 times 10 to 7 meter per second in a magnetic field of 6 times 10 to 4 t perpendicular to its path. What will be the radium of the path? What will be frequency and the energy in keV? Given. Mass of electron equals 9 times 10 minus 31 kilograms, charge E equals 1.6 times 10 minus 19 C, 1 eV equals 1.6 times 10 minus 19 J. Solution. Exercises Q5, page 249. An alpha particle accelerated to 10 MeV on entering a magnetic field of 1.88 t traces a circular path of radius 24.2 centimeters. Find the mass of the alpha particle. E equals 1.6 x 10 to 19 C, 1 eV equals 1.6 x 10 to 19 J. Solution. Exercises Q6 page 249. Two wires shown in the figure are connected in a series circuit and the same current of 10A passes through both, but in opposite directions. The separation between the two wires is 8 mm. The length AB is 22 cm. Obtain the direction and magnitude of the magnetic field due to current in wire 2 on the following figure. Segment AB of wire 1. Also, obtain the magnitude and direction of the force on that segment. Solution. Data. I1 equals I2 equals 10A, S equals 8 mm equals 8 times 10 to 3 m, L equals 0.22 meters. By right-hand grip rule, the direction of the magnetic field due to the current in wire 2 at AB is into the page and its magnitude is. Exercises Q7 page 249. A very long straight wire carries a current of 5.2 A. What is the magnitude of the magnetic field at a distance 3.1 centimeters from the wire? Solution. Exercises Q8 page 249. Currents of equal magnitude passes through two long parallel wires having a separation of 1.35 centimeters. If the force per unit length on each of the wires is 4.76 x 10 to 2n, what is I? Solution. Exercises Q9 page 249. The magnetic field at a distance of 2.4 centimeters from a long straight current carrying wire is 16 µT. What is the current through the wire? Solution. Exercises Q10 page 249. The magnetic field at the center of a circular current carrying loop of radius 12.3 centimeters is 6.4 times 10 to 60. What is the magnetic moment of the loop? Solution. Exercises Q11 page 250. A circular loop of radius 9.7 centimeters carries a current 2.3 A. Obtain the magnitude of the magnetic field A at the center of the loop B at a distance of 9.7 centimeters from the center of the loop but on the axis. Solution. Exercises Q12 page 250. A circular coil of wire consisting of 100 turns, each of radius 8.0 centimeters, carries a current of 0.40 A. What is the magnitude of the magnetic field at the center of the coil? Solution. Exercises Q13 page 250. For proton acceleration, a cyclotron is used in which a magnetic field of 1.4 Webers m2 is applied. Find the time period for reversing the electric field between the two Ds. Solution. Exercises Q14 page 250. A moving coil galvanometer has been fitted with a rectangular coil having 50 turns and dimensions 5 cm x 3 cm. The radial magnetic field in which the coil is suspended is of 0.05 Webers per square meter. The torsional constant of the spring is 1.5 times 10⁻⁹ Nm degree. Obtain the current required to be passed through the galvanometer so as to produce a deflection of 30 degrees. Solution. N equals 50 turns, C equals 1.5 times 10⁻⁹ Nm degree, A equals LB equals 5 cm times 3 cm equals 15 cm 2 equals 15 times 10 to 4 m2, B equals 0.05 Webers per square meter, theta equals 30 degrees. NIAB equals C theta. Exercises Q15 page 250. A solenoid of length Lm and 5 cm in diameter has winding of 1000 turns and carries a current of 5 A. Calculate the magnetic field at its center along the axis. Solution. Exercises Q16 page 250. A toroid of a central radius of 10 cm has windings of 1000 turns. For a magnetic field of 5 times 10 to 2t along its central axis, what current is required to be passed through its windings? Solution. Exercises Q17 page 250. In a cyclotron, protons are to be accelerated. The radius of its d is 60 centimeters, and its oscillator frequency is 10 MHz. What will be the kinetic energy of the proton thus accelerated? Proton mass equals 1.67 times 10⁻27 kg, E equals 1.60 times 10⁻19 c, EV equals 1.6 times 10⁻19 j. Solution. Exercises Q18, page 250. A wire loop of the form shown in the following figure carries a current I. Obtain the magnitude and direction of the magnetic field at P. Solution. Exercises Q19, page 250. Two long parallel wires, both carrying current I directed into the plane of the page, are separated by a distance r. Show that at a point P equidistant from the wires and subtending an angle theta from the plane containing the wires, the magnitude of the magnetic field is B equals sin 2 theta. What is the direction of the magnetic field? Solution. Exercises Q20, page 250. The figure shows a cylindrical wire of diameter A, carrying a current I. The current density in the wire is in the direction of the axis and varies linearly with radial distance r from the axis according to the relation J equals. Obtain a magnetic field B inside the wire at a distance r from its center. Solution. Consider an annular differential element of radius r and width drive. The current through the area dA of this element is. To apply the Ampere's circuital law to the circular path of integration, we note that the wire has perfect cylindrical symmetry with all the charges moving parallel to the wire. So, the magnetic field must be tangent to circles that are concentric with the wire. The enclosed current is the current within radius r. Thus, exercises Q21, page 250. In the above problem, what will be the magnetic field B inside the wire at a distance r from its center, if the current density is uniform across the cross-section of the wire? Solution.